So thank you for joining me and we'll get started. So just a bit of background, the Milwaukee Estuary AOC, for those of you who don't know it, is at the confluence of three major rivers within Wisconsin, the Milwaukee, the Menominee, and the Kinnickinnic, as well as Lake Michigan. Pictured here in dark blue, it receives discharges from various sources, including wastewater treatment plants, industrial operations, combined sewer overflows, and agricultural and urban runoff, meaning that aquatic biota inhabiting the region are likely exposed to multiple xenobiotics of various chemical classes. Practically, this can present a challenge for risk assessors and regulators when they're trying to figure out of the many potential detected chemicals, which ones are of potential ecotoxicological concern. So this kind of runs into our study objectives. First, we aim to identify the chemicals detected in the Milwaukee AOC. And then we wanted to prioritize these contaminants to help support risk assessment, regulatory and research efforts in the region. So you got a little bit of a preview for this in the keynote speech from Dan, but you can see that we carried out our studies at 8 sites in 2017, mostly across the Milwaukee urban region, shown here in magenta. And in 2018, we looked at 11 study sites within the Milwaukee AOC, adding 3 sites that are shown in black at various wastewater treatment plants across the AOC. In both study years, we carried out control exposures at the Great Lakes Ecotoxicology Division Laboratory in Duluth, Minnesota. So these exposures comprised of caged fathead minnows, which were deployed at study sites for 96-hour exposure periods, using the kind of a cage system as pictured here. So about halfway up the water column, we had 2 cages at each site, each containing 6 male and 6 female fathead minnows, for a total of 24 adult organisms per exposure site. At the end of the exposure period, we collected plasma, liver, and intestinal tissue, with a slight variation in terms of study years based off of the tissues we collected. And we carried out steroid hormone concentration analyses and gene expression analyses looking at transcript abundance of a variety of cytochrome P450 and UTD1A1 enzymes. At each site, there was an autosampler co-located to collect 96-hour composite water samples, which were used for chemical analysis, looking at nutrients, wastewater indicators, and pharmaceuticals, as well as in vitro bioassays. So we carried out a suite of adagene cis and transfactorial assays aimed at looking at pathway-related effects, and T47DK Bluc assays looking at endocrine-related activity in the water. So for just a brief overview about kind of what this looks like in terms of detected chemicals, in 2017, we detected 46 chemicals out of a potential 179 monitored for, and in 2018, a slightly higher amount of 77 chemicals at least one site. Over both study years, this left us with 83 unique compounds of varying chemical classes, including pharmaceuticals, pHs, flame retardants, industrial compounds, and pesticides, which we used for our prioritization effort. So overall, we wanted to take this chemical data and this effect data, including our in vivo and in vitro data, and use it to carry out a weight of evidence prioritization of our detected chemicals. I will mention one piece that I didn't include in this. There was a corresponding sediment detection study done in 2017 that we included as part of our chemical analysis. So what this weight of evidence prioritization framework looked like conceptually is kind of pictured here. Because we're using weight of evidence, we looked at multiple lines of evidence, including detection characteristics, environmental fate, ecotoxicological potential, and chemical effect covariance when we prioritized our chemicals. Within each of these lines of evidence, we had various subcategories, which were evaluated individually and characterized as I'll show on the next screen. So if you look at the overall prioritization effort kind of practically, this is what it would look like. So we developed a spreadsheet whereby within each subcategory, looking at our weight of our lines of evidence, we classified the chemicals as high, medium, or low priority, assigning a numerical score that varied amongst different classifications subcategories, depending on risk potential. And we then looked at the cumulative prioritization score of a single chemical across all these subcategories, which kind of gave us an idea of where the chemical lie in terms of risk potential within the Milwaukee AOC. To account for data limitations, we applied this equation here, which might be cut off at the bottom, but we basically took the cumulative prioritization score from our effort and normalized it to the maximum possible score given data limitations that may exist for a single chemical. This allowed us to kind of rank our chemicals from high to low priority and split them into practical groups, which I'll discuss in a second. So this next portion of the talk is going to be a hybrid of methods and some results highlighting specific parts of our analyses. So we'll kind of walk through it in terms of detection characteristics first. So for each of our chemicals, we evaluated spatial frequency, so looking at the percentage of sites that the chemical was detected in, temporal frequency, looking at the number of years a chemical was detected in, and environmental distribution, looking at the different compartments that we detected our chemicals in. So to give an example of how that worked with our data set, I'm demonstrating spatial frequency of our chemicals right here. In the high priority group, we had about 30 chemicals that exceeded detection frequencies of about 50% of sites, and they were assigned the highest prioritization score in this category. Following that, we had about 20 chemicals that were medium priority in this spatial frequency because they exceeded detection in about 20% of sites. And the remainder of chemicals in our data set were low frequency, being detected at less than 20% of sites. Again, we carried this out for each of these individual subcategories, which will be demonstrated when I show you the overall results of our prioritization. Moving on to our environmental fate analysis, we evaluated persistence, bioaccumulation, and biomagnification of each chemical detected, either using experimental data preferentially when it was available, and we gathered that from the CompTox knowledge base, or using QSAR estimates from EpiSuite, OPERA, and BMF-PRED programs. We evaluated persistence of bioaccumulation using ECA's PBT, VP, classifications, and we evaluated biomagnification as described by Gobin and colleagues in this environmental fate paper. And I don't know if it's cut off for you, but essentially we characterize chemicals as having a biomagnification factor of greater than 1 as likely to biomagnify in the environment. So what this looks like in terms of our data set, when we're looking at bioaccumulation specifically, we found that the majority of chemicals detected in the Milwaukee EOC were unlikely to biomagnify, with only 2 chemicals showing bioconcentration factors that exceeded the bioaccumulation risk potential in the ECA standards. And these were galaxolide and fluoranthene. So these were assigned medium prioritization scores. So moving next to our various benchmarks. So we used 3 different benchmarks in our ecotoxicological potential characterization. We compared detect concentrations to Canadian and US water quality benchmarks first, looking at criteria that were federally investigated and screening values that were just evaluated by different agencies. So we looked at this in terms of 2 different ways. First, in terms of the amount of detect concentrations that exceeded a water quality benchmark. So you can see here in the detect concentrations in black, if more than 50% exceeded a benchmark, as we see with pyrene, that would be considered high risk within this prioritization subcategory. And then we also looked at benchmark type. So going from potentially the lowest, most conservative benchmark of a chronic screening value to the least conservative benchmark of an acute water quality criteria value, we assigned different risk potentials associated with exceedance of these. So if you look at pyrene, we can see that it only exceeded a chronic water quality criteria, so we would give it a medium prioritization score. But benzoate pyrene exceeded an acute screening value, so we give that value a higher water quality benchmark type prioritization score. We also compared our detect concentrations to in vivo effect concentrations derived from the ecotox knowledge base. And when that data wasn't available, we used QSAR estimates from TEST and EcoSAR programs for data limited compounds. For our ecotox benchmarks, we used 2 benchmark types. First, an unadjusted benchmark was just a minimum in vivo effect concentration, shown here in red, and an uncertainty adjusted benchmark, which had various application factors assigned to it to account for uncertainties associated with endpoint of minimum effect concentration, study length, and data richness. We were able to compare all of our chemicals to water quality benchmarks or ecotox benchmarks derived in this way. And we again evaluated against exceedance frequency and benchmark type when evaluating ecotox benchmark exceedance. Finally, in terms of our benchmarks, Dan mentioned this nicely. We looked at ToxCast benchmarks, comparing our detected concentrations to in vitro effect concentrations derived from the ToxCast database. So this looked a little bit different. We used a cutoff threshold of 10 to the -3 for exceedance frequency in this case. And again, evaluated the number of detects that exceeded our various ToxCast benchmarks. We also, however, looked at the number of chemical assay combinations exceeding ToxCast benchmarks to characterize potentially affected pathways. So for example, if we look at these two flame retardants at the top, you can see that one of them had a high number of chemical assay compounds exceeding that threshold cutoff. And that would be given a higher prioritization score than the other one, which did not exceed at all, or this triethyl citrate, which only exceeded in three chemical assay combinations. So for our final category of prioritization, we looked at covariance of our chemicals with measured effects. So those in vitro and in vivo effects I mentioned at the beginning. We split our measured effects into general endocrine-related and xenobiotic metabolism-related effect subcategories. And then we identified which effects were statistically significant at least one study site across study years. For those significant effects, we then used random forest regression to generate predictive models, and then recursive feature elimination to identify important chemical predictors for each effect. We then examined partial dependence plots to determine the direction of the covariance, flagging chemicals as having positive or negative covariance. To kind of mitigate potential uncertainties associated with individual models, we then prioritized our contaminants by looking at a weight of evidence across these individual models within endocrine-related and xenobiotic metabolism-related effect subcategories. So for example, if you look at gabapentin here, it's a little bit small, but you can see in the endocrine-related subcategory, there were 2 out of 4 effects that demonstrated positive covariance. For us, that indicated a high prioritization score within the chemical effect endocrine-related covariance subcategory. So that was a lot of methods, and now we have a couple minutes for results. So here's what I'm going to show you. So when you put all of this together, it either comes out as this heat map here or a big spreadsheet with numbers that you can look at individually in terms of what drove your overall prioritization. From this, we were able to identify out of the 83 compounds, 7 potential high priority compounds with prioritization scores exceeding 50%. So this included 2 sterile compounds, 3 PAHs, atrazine, and venlafaxine, which is a pharmaceutical.
Erin, about 3 minutes left.
Okay, sorry about that. I'll give a little bit for questions, I hope. We were also able to identify several low priority compounds, which had overall prioritization scores of 0. So this included several methylated PAHs, several pharmaceuticals, and a couple industrial products shown here. And finally, you'll see that there's gray italicized chemicals all the way through this slide, and those are data limited compounds. So compounds with severe ecotoxicological data limitations, which may have impeded our ability to prioritize them. So what this looks like overall is we were able to take those 83 chemicals detected in Milwaukee S3 AOC and highlight 6 high priority compounds, 14 low priority compounds, and 9 data limited compounds, essentially breaking down our 83 chemicals into 6 compounds that definitely need further evaluation within the Milwaukee AOC, 14 compounds that within this watershed may be able to be tabled for now, and 9 compounds that require further investigation before they can be adequately prioritized. As I spent a lot of time demonstrating, we also use this to develop kind of the basis for an alternative prioritization framework that can be employed or adapted to transparently prioritize contaminants within freshwater watersheds. So I thank you guys for your attention and thank the conference organizers for setting this all up.